Gianmarco, if you want to share your screen.
Absolutely, I can. So thanks, Marco. Let me see if I can share my screen. Okay. Can you see my screen?
Yes.
That's great. So before I start, I want to thank the organizers of this event because this is the title of my presentation, what's so unique about TinyML. But I need to be honest. So if TinyML is so unique, is also because of you, because of these initiatives. And we need probably do have more of these incredible workshops with such interesting presentation that you're going to see in the next few days. So my name is Gianmarco Iodice. I'm a Gen AI lead at ARM. Don't worry, I'm not going to talk about Gen AI, apart maybe in just a few slides. But I'm also the author of the TinyML cookbook. I love TinyML, and I really hope with this presentation, where I'm going to answer this question with you by looking at the past, the present, and a bit of a future. Because trust me, TinyML is a field like no other. And I will start, well, I talk about Gen AI. I also saw something, an interesting presentation also in this workshop, but I'm not going to talk about Gen AI because this presentation will be about TinyML. So why do I have a slide reporting a generative AI or a large language model running on mobile here? Well, I'm not going to answer this question now, so you need to stay until the end because at the end of this presentation, I will tell you why TinyML is so connected to generative AI, or better, Tiny AI. So let's recap TinyML. Okay, so I want to have everyone fully aware of what is TinyML, but also to understand what I'm going to present today. So TinyML is the technology that wants to bring this intelligence to objects around us, so in everyday objects, but with a focus on power consumption, data privacy, and cost. So these are the three areas, in my opinion, that make TinyML so appealing, so cool, so unique. But what is important to understand is why. Why do we have this focus? So why TinyML is focusing on this? We all know the potential of machine learning, what machine learning can provide. However, machine learning alone is not enough to scale applications powered by ML. I mean, think about the infrastructure that you need if you want to have a very powerful machine learning. For instance, let's use a very pragmatic example. For instance, I'm in the city. I want to monitor, for instance, the number of cyclists on the road. Okay, in order to also plan advanced initiatives to maybe make the road safer. Okay, so there are many ways you can build this kind of use case. Well, certainly you can build an infrastructure where you have internet connectivity, you have sensors, but with TinyML, we can make, for instance, this very simple use case, very simple, cost-effective, because with TinyML, your device do not need, for instance, cables to operate because can be battery powered, and do not need an internet connection. Why did I use the example of cyclist counter? Because a few days ago, I was walking here in Cambridge and I noticed a few cameras around with a warning say, well, there is a camera, but actually we are not recording any frames we are just counting. So these devices are actually deployed everywhere in a very non-intrusive way. And as I also preserving the privacy. And this is a very, very cool use case. Then we can also see in our cities. So the ingredients of TinyML are these. So this is the definition I provide in the TinyML cookbook. So this is a set of technologies. So it's not just about ML, it's not just about embedded system, because we need both to make smart applications on low power devices. And we will also see what kind of low power devices we can have. Generally, these devices, in order to be low power, they have some constraints. They have, for instance, limited memory. They have also limited computational capabilities. But these limitations won't make these devices less capable to perform ML at the edge. But a cool and very interesting aspect is about the sense or the sensor that are attached to these devices, because most of the time these devices are with sensors in order to have a feeling of of the environment of these devices are working on. And it's through these sensors that machine learning algorithms most of the time that we need to make decisions. A couple of years ago, I attended a presentation, and one interesting definition I heard in a very single sentence was this: a level of computing on top of sensors to allow smartness in a minimal intrusive way. And this is exactly probably the right definition, right? So it's something that we're gonna have by default probably on our low power devices in order to allow this smartness. Applications, well, applications powered by TinyML are endless, and probably most of all of us, well, we assume that it is just ML, but actually TinyML by all means. Because if you look at the smartwatch, well, the smartwatch has plenty of use cases powered by TinyML applications. Well, already, I mean, the recognition of the activity, of the physical activity, for instance, is a very interesting TinyML use case. But also the smartphone itself, right? It contains TinyML inside, for instance, for detecting the keyword for starting to interact with the devices. I'm not talking VR and VR because there are many TinyML applications also in that case, including drones. And also last year, the TinyML EMEA 2023, there were very interesting presentation where Michele Magno delivered some presentation about these tiny drones, right? They can fly. These are very interesting. So I really recommend to watch it. But applications are not just about consumer electronics, because before I mentioned mainly consumer electronics, but what makes it very interesting, Talema, is the fact that we can deploy these devices on a very large area. Remember, I talked at the beginning scalability, and this is actually one of the key aspects of TinyML, because imagine a very large field. Well, you don't want to have cables around, okay? You don't want internet connection. Probably internet connection can be, well, quite difficult in some contexts, right? You want basically these devices to operate autonomously and maybe interact with other devices near them, okay? And they can propagate information maybe to a server, which might be miles and miles away, okay? Scalability is the key to unlock some of the use cases, for instance, for agriculture, or for instance, for detecting fires in forests. Today, I'm going to talk mainly about microcontrollers because this is my area, but microcontrollers are not the only devices where you can have TinyML, because that is the reason at the beginning of this presentation, I mentioned low power devices. But this is the area where I'm working on, and that is the reason I'm mainly focusing this presentation around microcontrollers. But why TinyML on microcontrollers? Well, first of all, these devices are designed by nature to be very power efficient. So this is their goal, to deliver computation in a very power efficient way. But probably the most interesting aspect are the fact that microcontrollers are already deployed everywhere in many industries: automotive, consumer electronics, healthcare, agriculture. And here I have reported an impressive number about the number of microcontrollers sold everywhere, worldwide in 2021, 31.2 billion devices. Imagine if we could have ML on all of these devices. Does it scale the technology? Probably yes, right? And trust me, this is absolutely doable. Well, the other aspect is the low cost, and I'm gonna provide an example later about low cost, because sometimes when we think about very cool project, very cutting edge technology, we think, well, this is probably will require a lot of money to be done. Well, for TinyML, this is not true. Programmability is probably the other selling point for microcontrollers, because these are very easy to program. However, when we mention about TinyML, and here we enter the phase where I'm looking at the past, my personal past, probably we can go also far away from 2013, and that is the first time I actually heard about TinyML. I was a student, and at the beginning of the lesson, the professor was saying, well, if words could talk, and it was the lesson about ambient intelligence, machine learning on low-power devices, already in 2013. So TinyML-24 is not something that happens, is a today's technology. Is a technology that we had already 10 years ago, but simply nowadays is a lot easier to be deployed. And let me look at 2013, right? 10 years ago, 11 years ago. Let's look at the software development and the machine learning aspects. Microcontrollers were very difficult to program compared for sure to nowadays microcontrollers. Well, I remember they were using C, but in some cases also assembly, but probably the most difficult aspect was the portability of the code among different microcontrollers. The other aspect is about the IDE that could not offer a very plug-and-play experience. It was also a bit opaque in order to have these microcontrollers programmed on a device. What about ML? Well, ML was already a thing in 2013. So ML is not a new thing. There were already interesting algorithms of machine learning, and I'm not talking about deep learning here. I'm talking about, for instance, decision trees that already are also in 2024 can be used, for instance, to deploy very interesting use cases. Very small models, but the big problem were the fact that most of these open source frameworks that we have nowadays, we didn't have in 2013, or very, very few. Furthermore, we didn't have end-to-end tools to make ML design straightforward. So it was a very difficult, and maybe just for a few that knew, for instance, how to program microcontrollers and how to train a machine learning model. But what could we tell about the hardware capabilities? Well, very interesting. I have an example exactly from 2013, and that was a personal project. That was an MP3 player that I built from scratch in C. I cannot say it was probably a very, very easy task because it was very complex. It involved also a bit of assembly. But as you can see, actually, the UI is quite smooth, right? And I'm talking about 2013. And if you look at the specs on the right-hand side, you have the program memory is more or less what we already have, 512 kilobytes. The SRAM, absolutely, maybe a bit higher today. But regardless of these limitations, well, I could actually have a UI, a very smooth UI up and running, and the UI is quite complex, and there are also very similar algorithms to machine learning. For instance, the anti-aliasing or other subsampling algorithms, which are also you can also find in deep learning models, for instance. So what happened from 2013 to 2023, 2024? So, well, the software and ML changed and made everything very, very simple. So the software development changed because now microcontrollers are very easy to program. Well, also with Python, the ideas of a plug-and-play experience. And for instance, in the book, I try to provide some guidance to have this plug-and-play experience where you don't need to install drivers. Okay, you just need to plug your microcontroller, and you can also, in some cases, copy the binary to the microcontroller, like in a very similar to a USB device. But the other interesting aspect I very like it is the code portability. I write a code from one microcontroller. I like the same code to work on other microcontrollers. I don't want to rewrite my code several times. And this is actually probably the thing that I like most. About machine learning, well, there are many free open source and very easy to use frameworks. And some of these frameworks, they also offer end-to-end tools. I don't want to mention something particular, but trust me, there are many frameworks that they allow you to have machine learning, software development very, very easy. Who do we need to thank here? Well, the open source community and academia, because these two entities made this very, very simple. With these two key contributors, we could not have SciTinyML in this shape, I would say. But when the technology scales, this is a sentence actually I grabbed from an interaction with UNICEF. Well, when the technology scales, there are often huge opportunities to solve real-world big problems. And in 2021, I met Dr. Paolo Bombelli from University of Cambridge in Cambridge because he was delivering a presentation for the TinyML at the TinyML meetup there in Cambridge. And he was talking about a very fascinating device that can they can generate electricity from photosynthesis. This is absolutely, incredible. So a device that can actually take the energy from the sun and can generate electricity to power devices. Well, you can say, well, this looks very similar to a solar panel. So I have already the solar panel. Why do I need to care about this device? Well, in this second slide, you can probably notice one interesting aspect. Apart from the current that we can generate with this device, which is honestly much lower than a solar panel, but there is an aspect that makes this device very unique, is the fact that can generate electricity also during the night. How this is possible? Well, this is actually a device made of algae. Algae is a plant. Well, plant, they survive during the night, right? And that is one of the reasons why this device is actually quite good, because it can also generate the electricity, give a power, also in absence of light. Okay? And this is actually very cool. Paolo came there at the TinyML, we discussed, and we said, well, what if we could have a machine learning applications powered by this? That would be very cool. Well, if you think about this, you can say, well, this generates a very little power. Well, this looks a very difficult problem to solve. Is it true? Not at all. Because after a few chats with Paolo, we also understood together that we could actually have a microcontroller, today's microcontroller, a cancer microcontroller, powered by this device that nowadays can only power small electronic devices. Don't think about this as the solution, because of course there is a lot to do with this device. But certainly it can power microcontrollers or devices with low power compute capabilities. So here, yeah, we presented together this project with the idea to provide trying to have a sustainable device. So we wanted to build a device with the local algae. Okay, so try to imagine to have these devices, for instance, in remote regions, and we didn't want to use battery, maybe use the algae from the river of that region. Well, the potential applications for this are mainly in rural areas in order to provide energy longer than traditional batteries. For instance, application that can last in theory years, right? Because using the algae of the local river. And together we decided to set a project, okay, project to monitor the weather condition and the water quality using SciTinyML in the River Thames in London, using the native algae of the river. So without using other batteries, simply going to River Thames, take the algae, building the device, and use this device to power a microcontroller. And that was actually from what we knew, the first ML applications powered by algae on a microcontroller. But the overall goal was this. It was not just about, oh, we have power machine application with algae, but actually to demonstrate to the community, to the TinyML community, they don't need that regardless of their experience, they have the open source community with them, because this project was actually built in 2 days using the help of the open source community in a very, very affordable way. About the machine learning deployment framework, for instance, there are many options. The only thing maybe to say about the framework is about well, the device we're going to use for this specific application will be very constrained in terms of memory. So you need a framework that can provide at least ahead-of-time capabilities. Ahead-of-time capabilities means that you have your machine learning model, but you generate your code for running your machine learning model ahead of time. So before deploying the model on the actual device. So when you look at this, you don't have many frameworks there, but maybe deep learning compiler frameworks are actually quite good to solve this task. But that was our solution. Honestly, nothing very crazy. It was just a microcontroller, a consumer microcontroller from ST Microelectronics. It cost 1.7 pounds. We bought the adapter in order to solve the microcontroller, and we actually managed to connect the algae device and to power this device with the algae. As you can see, there are very important constraints here in terms of flash and SRAM capacity. But regardless of these constraints, we were able to build our TinyML application. Well, remember that there are also very other interesting aspects about the sustainability. So sometimes we take for granted that I need a microcontroller, but I also need a very powerful laptop to program a microcontroller. And in some countries, this is probably quite challenging, okay? Because it's difficult to have expensive laptops. And here we have expanded the project and demonstrated, well, you don't need a very expensive laptop. If you have a Raspberry Pi, you can use the Raspberry Pi to program the microcontroller. In total, I mean, this solution can cost 50 pounds, more or less 40 pounds, the Raspberry Pi, plus something for building for creating the microcontroller board. And that is actually quite fascinating, because I want to stress this aspect is all about the open source community, that is possible. The open source community is driving this effort. What did we develop at the end? So we developed a model from an example that Pete Warden and Dane Situnayaki delivered. Well, at the very when they launched the TinyML term, right, in the community with their Hello World example. We demonstrated the possibility to run this tiny machine learning model on this microcontroller powered with the algae. And as you can see, I have reported also the current consumption, which is very, very small. It's around 1.8 million per. But I'm pretty sure that also even low power devices out there can also go well beyond this limit. And here I have reported a few images from this project. What is this about? This is actually a floating device where you have the algae connected to build the anode and cathode, and this big device can generate sufficient energy or power for the microcontroller. And that was there on the river Thames for a few months, and the team University of Cambridge and they started monitoring also the activity of these devices. It was actually a very fascinating project, and with a very little effort from our side, from a SciTinyML perspective, because actually the effort was very, very little. So what about new use cases? So certainly I can say that microcontrollers are more compute capable and power efficient than 10 years ago. And if we look at, for instance, a modern microcontroller, you can also find neural processing units which are very capable to run efficient AI solutions, AI or machine learning solutions. Here, for instance, I have reported a slide for the computational efficiency for the ARM Ethos U85, not 65. I had a mistake in the previous slide. Here you can see that actually the computation is very, very, very much more efficient, for instance, from the previous generation. So compute capability is great. However, what can we tell about the memory? Well, memory did not evolve at the same speed. I would say that the pace of memory storage development has been steady probably for the last 10 years. Right. So we have seen compute capabilities evolving quite fast. I mean, microcontroller much more efficient. In terms of memory storage, we are more or less at the same level 10 years, maybe a bit bigger, although these memories are certainly much more power efficient and probably faster than 10 years ago. But if you look at the spectrum of microcontrollers out there, you can see probably more or less the same ranges for the SRAM and the flash. And here I have reported a slide where I summarize the landscape of RAM size for microcontrollers, mobile phones, and laptops. I have kept voluntarily the cloud out because I wanted to focus just on the edge, right? Where on the left-hand side, you have the very edge, the tiny ML space. On the right-hand side, you have the laptops, probably the end, or what we can consider, for instance, an edge device. Well, if you look at the microcontroller, you compare microcontrollers with mobile phones, you can see there is a gigantic gap between these two devices, right? So it's a lot. So you have a very, very small RAM available for running ML applications. The gap is smaller between mobile phones and laptops. In some cases, they use also very similar technologies. But certainly microcontrollers are the tiniest, or well, there are also other devices, certainly, but the gap is quite big. So modern devices are certainly able to run ML applications more efficiently. However, remember that we want scalability, and we want also to deploy new use cases. So it's not enough to learn, for instance, use cases from, for instance, from 4 years ago. So the community wants to deliver newer use cases on these devices. And certainly the open source community, first of all, tailored some of the models, for instance, for image classification, object detection, for memory constrained devices. Because in my opinion, the migration from large to tiny happen in two ways. One is certainly by tailoring new models for tiny devices, and there are many options. Here I just reported 2 of them, but there are very other cool projects out there that make the models very, very efficient on microcontrollers. For instance, MobileNet and EfficientNet for image classification, or the faster objects, more objects from Edge Impulse for image detection, or for object detection, sorry. But models are not enough, because here you have seen the big constraints on the memory, right? Compression techniques and lower bit precision were actually the keys to bring new ML models to microcontrollers. And here there are many techniques, the clustering and pruning, knowledge distillation. What I very like is actually the 8-bit quantization, but also the lower bit precision. In terms of lower bit precision, what can I tell you today? Well, certainly the community in the last couple of years were focusing on 1-bit quantization. There were also interesting presentation at SciTinyML you made last year, and 4-bit quantization. Well, 4-bit quantization, and it means that we use only 4-bit to represent the data. So on the left-hand side, you have the raw data and floating point 32. On the right-hand side, you have the integer 4 data. So it means that you use only 4-bit to quantize the single floating point 32 value. And here, there is no so there are many ways you can do it. So the quantization can happen in a different way. For instance, you can have one quantization value for the entire array that I want to represent, or you can split the array in chunks or blocks of fixed size, and you assign a scale a quantization parameter for each chunk in order to have a better to avoid accuracy loss too much. So you have this is quite important, for instance, when you have a very large array and you want to represent to integer 4. So one way is to split the array in chunks, and you have a quantization parameters for each chunk. But why I'm stressing the 4-bit quantization at this stage? Well, we are all aware of what is happening out there. So this is probably the generative AI area. And probably everything started, well, it started probably earlier, but in November 2022, we have seen actually what these models could, or large language models in particular, could actually do. I provide a question to these models, and these models are able to generate an answer. These models are very sophisticated, extremely sophisticated, but also extremely large. And I don't want to say that these are unsuitable for microcontrollers, but at least I want to say that are very, very difficult because, of course, they contain a kind of knowledge. Well, the bigger they are, of course, the more they can retain in terms of knowledge. So at the moment, large language models are quite difficult, although there are some interesting attempts to make also LLMs running on microcontrollers. And here I have reported a few models of the open models. So I'm not talking about proprietary solutions, where you can see also the size. Well, we're talking about 70 billions, right? The trainable parameters. So which means in floating point 16, 140 gigabytes. Well, this is way beyond microcontrollers, but also mobile devices. Well, also is quite challenging also for a cloud infrastructure. And here I have reported some models from Microsoft, some models, for instance, from Meta, from Google, and so it has highlighted with the colors. What can we tell about these large language models if we want to deploy them on mobile devices? I'm not talking about microcontrollers, I'm talking about mainly mobile devices. Well, here we have exactly the same type of constraint as SciTinyML, which is the memory. The scale is different, certainly is different, but the constraint, the type of constraint is the same. And if we look at the video, at the beginning, I reported the video where I demonstrate a large language model running on a mobile phone. Okay, here I have reported one model is a Phi-2 with 2.7 billion devices. If this model runs today on mobile phones, it's because of what we have done in the SciTinyML field, okay, so far. Because nowadays that the open source community is driving also a different compression techniques and are all coming from what we have seen in TinyML to deploying TinyML models. And here I have reported the integer for estimated memory usage. I mean, as you can see, on a mobile device, you can also have up to 7-8 billion large language models, which are quite sophisticated, I would say, and they can only consume 3.5 gigabytes. If you consider that on average, a mobile phone has an 8 gigabytes of RAM, this is actually quite doable. And this is the spectrum of what models for mobile and edge deployment we can actually have it nowadays. And why? Here's the same thing I mentioned at the beginning about TinyML. To easily scale applications powered by ML, remember that the more infrastructure you put in place, the more complex this problem becomes. And this is true for TinyML. This is also true for large language models. If you keep everything local, everything becomes so simple that we can scale the adoption of this technology. And again, when technology scales, there are often huge opportunities to solve real-world big problems. And that was a presentation delivered with the Tiny AI Forum last month, where with UNICEF, we collaborated to understand how we can deploy LLMs to solve a problem in education. This is still ongoing, so we are trying to address this problem or to inspire also the community in particular. And here, everything started from a conversation I had in August last year, where with other companies and with UNICEF, we were trying to shape the educational tech for good curation framework. If you look at education nowadays, there are many educational technologies and tools, and some of these are also powered by TinyML. But the most difficult aspect for governments and for organization, also from people, is to understand the impact in learning. And they decide to create this framework to actually score these tools that are required for education. But one aspect and one question was, well, how can we help kids learn new technologies or programming languages in a very scalable way in the global south? Well, someone can say, well, why don't we build a very cool robot, for instance? We can make it also very cost effective, and we ship that and they can learn with a robot how to do programming. Is it enough? Well, probably not at all, because if you don't have the right people to teach the technology, of course, the robot is only a toy, is not an educational tool anymore. Because in order to have a very scalable learning experience, we need the teachers, the educators that need to know the technology and the robot. And this is summary of what I have just said. So how can we help teachers in the global south to be, to learn, to have this continuous professional development to help them broaden their knowledge? Because this can be quite tricky if we want in person every time to go there and teach them how to use the technology. It does not scale at all. Well, large language model, Gen AI in particular, at the edge, could be a very interesting opportunity to enable these teachers and to have this continuous learning. But of course, the question from UNICEF was, well, where we are with the technology, because we cannot look at the technology in 4 or 5 years' time. It's too late. We need not today's technology, we need probably also the past technology to work well. And the answer was, well, actually, we can already run these models and also on the Raspberry Pi. And this is also a presentation that Pete Warden delivered at the Tiny AI Forum. Also here at TAM, we did some experiments, and we can certainly say that we can run it also on Raspberry Pi. And if they run, is because of what we have done so far in the TinyML community. So what's so unique about this TinyML field? Well, these are the three keys, in my opinion. The first, TinyML holds the answer to AI everywhere. This is the technology that we need to be aware in order to open opportunities from business, but also from a sustainable perspective. So this holds the key to have everywhere AI. The other thing is, and I hope I managed to provide a practical example, is that we can bring to life real projects with just a few dollars. We know that in some, for instance, in some universities, they have also, we don't have a lot of budgets to create projects. Well, TinyML is actually the right technology because we don't need a lot of funds. We can build very sophisticated projects. I'm not saying with just a few dollars, but definitely with a reduced budget. And the third that probably I like, this is probably the aspect I like mostly, is the fact that TinyML is the excellent field for learning embedded programming, but also machine learning. And why? Well, because TinyML is driven and it thrives on the contribution of the open source community. And I'm gonna close this keynote session with this. So thanks everyone for being here. It was actually a very good pleasure, great pleasure.
Thank you so much. Thank you so much, Gianmarco. I think on behalf of all the participants, that was really an excellent keynote, a lot of food for thought. So let's see if there's any questions for Gianmarco or any comments. I saw there was one comment from Marcelo in the chat, but you covered that already about the using the Raspberry Pi. Yeah. So that's Amied, please.
Yes, hello. So the restrictions in this field are not only the memory and the RAM that we possess, but I think also the weight and the volume. In some industries, aviation, automotive, weight and volume are very important. Or in Elon Musk brain chip, for example, one cannot put a big device. So I think one should weight and optimize all these factors. For example, in the automotive industry, they are sometimes forced to use ECUs, electrical control units, which are heavier, 1 kilo, 2 kilos device for the automatic gears, for example, because they are more robust against vibrations, against heat, against many other factors. So it's just a comment. Thank you.
And that's actually a very good comment because I haven't reported one of the benefit of these devices. I mean, these are designed to be small, are tiny in terms of memory, but you're absolutely right. Are also tiny in terms of physical space. And that is the reason in many industries, because they can be placed in many appliances, for instance, because these appliances, or as you said, in automotive, we have also constraints for as physical size and also weight.
There's one question in the chat from Naziru, which is asking, what is the technology behind the TinyML power efficiency?
Okay, what is the power efficiency? Well, certainly, well, in order to get very power efficient device, you need to make some compromises. I mean, there are no very big tricks. Certainly, first of all, you need to probably sacrifice something. For instance, some of these devices, you might not find a floating point unit, just to make an example, right? And you need to provide in some cases, solutions for the specific use case you want to try. For instance, if you have, in the example of the algae, I had to use a very, very low power device, that actually was low power, but also very with less memory compared to more sophisticated microcontrollers. This is a compromise, everything. You want to be more power efficient. Of course, you need to have to leave on the table some of the capabilities you have. The other aspect, believe or not, is in the hands of developers, is the software. It's not just about hardware. The efficiency also comes in a way you write your software. And compression techniques, for instance, are crucial not just for to fit the problem on the microcontroller, but also to reduce the memory traffic to and from the memory, which is most of the time the most expensive thing. So, and these are more or less the things. So it's a software and the hardware. How we say, the software hardware co-design, right? So these are the things.
Gianmarco, did you publish a paper about the algae deployment?
So for the algae, there is a paper from the University of Cambridge concerning this project. No, we wanted just to provide a tutorial once this stage of testing has been completed. So we will also provide a step-by-step approach to replicate this example. As we said, we want to make the open source community part of this project.
Excellent. I think we have time for one last question, which is about using TinyML in designing nanosat. Nanosatellites. I think we have a presentation. We had a presentation last year from Antonio Bagur, which is from Guatemala and now working for Arduino, which was exactly about nanosat. But maybe Gianmarco, you have some other information about using TinyML on satellites.
Unfortunately, not that much because I'm not heavily involved in satellites technologies. I know it is used, but I'm not very exposed to satellites technologies. I'm more on the art at the moment on TinyML here. But I'm pretty sure there are also many other opportunities there. Well, I can think of quite a lot. Power is the key to unlock many use cases, and I believe is also there.
Super. So thanks again. It was a wonderful keynote. And of course, I mean, we're going to be here the whole week. So feel free to, join at any time. And we'll be more than happy to get your comments and your feedback about presentation.
Absolutely.
Thanks again, Gianmarco.
And thanks again for inviting me, and thanks to the organizers to have organized this such a very big and important workshop. Thanks, everyone.
Thank you very much. Thank you, Gianmarco.